Hi, in this video we're continuing our discussion with Chapter 12, Section 2. Specifically, we're going to be talking about unit vectors. So in the previous lessons we talked about what is a vector, what is a position vector. Now we're going to be talking about unit vectors. So the idea of unit vectors, if you learn nothing else from this video, is that a unit vector, maybe we should have defined it first, but too late. A unit vector is pure direction. In the last video I mentioned that when we're done with this, you're really going to be thinking about vectors as direction, as a more useful term of direction, especially when we get into higher dimensional spaces like 3D space or 4D space, etc. Definition: a unit vector is just a vector with length 1. Okay? Nothing controversial there. But to go back to the idea is that any non-zero vector has an associated unit vector. I'll talk about non-zero vector in a second. I guess we haven't talked about the zero vector in these videos yet. It'll probably be pretty clear to you. But so, given V, the unit vector in V's direction is, you take V and divide by the length of V. So again, if you can't read that notation, you should write it down. We're going to take the vector V and divide by its length. So when I was talking about dividing by length, maybe that's where your alarm bells are ringing about 0. It's also that the zero vector is going to have length 0. Again, I'll show that in a second. Let's do a brief example of this. If V was the vector negative root 3 comma 1, right now you should be able to find the length of this. You should be able to find its slope. There's lots of easy things you can do with position vectors. We don't really need the slope. Again, the vector will be its own direction, so to speak. The length of V, you should be able to do this. Can you do it quickly? Should be 3 plus 1. Has a length of 2. So, if I did my unit vector conversion, if I took V and I divided by its own length, what am I going to get? I'm going to get negative root 3 over 2, comma 1/2. Because a lot of these unit vectors are going to be fractions, we're usually not going to write them like this. It's going to be annoying to write this. So sometimes we factor out the magnitude or 1 over the magnitude and just write this as a scalar multiple of the original vector. Hint. It's a scalar multiple of the original vector. That's a spoiler, more or less. My claim, real quick, I'll just say we just literally took the components of V and divided them by 2. I hope you're okay with how we got this. My claim is that this is a unit vector. Let's find the length of it. If it's a unit vector, its length should be 1. Don't get worried about having these length notation and the length notation. No big deal. That would be 3/4, that first component squared, plus 1/4 which is 4/4 or 1. It is a unit vector. Just one more note. We usually use the letter U for unit vectors. And use a hat notation. So U hat would be a unit vector. So we are saying that if you saw this notation, it should waggle its eyebrows suggestively at you and say, I'm probably a unit vector. Look at my hat. Look at the letter they decided to use for me. One more example. A little trickier. Find the unit vector in the opposite direction of v equals -5, 5. Right? No big deal. You should be able to do this. There's lots of thinking about here. You could either reverse the direction first and then turn that into a unit vector. I'm just going to go for it the other way. First, find v over v, the vector divided by its magnitude. What does that require? We need the magnitude, which is 25 plus 25, root 50. I don't care too much about you simplifying radicals in this course, but this is an easy one to simplify. It's going to be 5 root 2. This will help us when we're talking about the next lesson. So again, normally what I would do is write it like this. 1 over 5 root 2 times my original vector, -5, 5, like that. That's one way to write it. But just for kicks, I'll show you it's this. If you simplified everything, it would look like this, which is important. If you compare this one to our last one, if you compare this unit vector to this unit vector, you should start to see some things that are helpful that we'll talk about in the next video. So, U in the opposite direction, how do we reverse direction? How do we reverse direction? We're just going to multiply by negative. -1. Opposite direction. Okay? That's it. That's all there is to the unit vectors in the opposite direction. This does allow us to define another important idea with unit vectors, namely standard basis vectors. So standard basis vectors, we're going to define two specific vectors. We're going to call them I hat 1, 0 and the vector j hat, which will be 0, 1. Can you draw these? They're both position vectors. Can you draw them? So I hat position vectors will start at the origin and it will go 1 unit along the x-axis. That would be I hat. J hat would be starting at the origin and going 1 unit along the y-axis. And that's what they look like. Now, maybe this doesn't clarify why we're using them, why they're useful. That's what I wanted to say, why they're useful. But I will be like, think X direction stuff. And this will be true when we move back to 3D, so please pay attention. And J is thinking Y direction. So I usually draw that little hat in place of the dot that both those characters would have in normal English writing. You can put the dot. Some students stressed out about that. It's totally okay. Why are they useful? So why are we talking about this at all? So any vector can be written as a sum of scalar multiples of I and J. What do I mean? So an example of this would be if I have 3 comma negative 5, isn't it true based on what we know so far that that's the same as taking 3 comma 0 and adding it to 0 comma negative 5? And then I'm going to factor out some scalars here. Isn't that the same as saying 3 times 1, 0 plus, I'll write it this way, you'll see in a second, negative 5 times 0, 1. And then if I'm using that notation, isn't this 3i minus 5j? And that's what we're talking about. So this vector, our vector in component notation, can be translated to standard basis notation. Okay, as I and J notation is usually what I would say it. So the idea here is, this is the idea of what this means to be a basis, of a standard basis. You would learn more about this in your linear algebra class, but realistically, the basis you're used to, the standard basis, works like this. It'll be 3 steps in the I direction or the X direction plus minus 5 steps in the J direction. Why is it minus? Because instead of going toward the positive y-axis, we're going to go away from the y-axis. We're going the opposite direction. One more example of this would be something like if A equals 3 comma negative 2 and B equals 9 comma negative 6 and C equals negative 3 halves comma 1. Okay. I want you to do 3 things here actually. I want you to write this, write each vector as standard basis vectors, okay? I and J stuff. Hats, let's do hats. 2, I want you to find their slopes. Sorry, I guess that was 1 up there. And then 3, find their magnitudes. You should be able to do all 3 of these things pretty quickly, but why don't you pause the video right now and see. I'm assuming you paused it. 3, 2, 1. Part 1 should have felt very easy if you understood what we were just doing. A would be 3i minus 2j. B would be 9i minus 6j. And C would be negative 3 halves I plus j. Usually we would leave off the 1. If you wrote the 1, it's fine. In this class, both notations are going to be just fine. I don't have a preference of one over the other. You need to know both. You need to be able to translate both into whatever notation you prefer. But otherwise, do what you want. As long as you can read them, you're fine. Slopes might be the one that you had to turn back in your notes and look. The slope of A should be negative 2/3. The slope of B would be negative 6/9. And really quick, if you simplified that, you would start to notice something that's also negative 2/3. Are you quickly fixing your slope for C? 1 divided by negative 3/2. If I multiply by the reciprocal, I'm getting negative 2/3. So what does it mean if these vectors have the same slope? What does it mean if these vectors have the same slope? What it means is they are parallel. Oops. So A, B, and C are parallel. Hold on to that thought for a second. Let's do the magnitudes. The magnitude of A is actually going to be 9 plus 4, root 13. The magnitude of B would be 81 plus 36, which is 117. And the magnitude of C would be 9/4 plus 1, should be root 13/4, or root 13 over 2. Yeah, I'm pretty sure that's right. So I want you to notice something. Can you find the unit vectors? Can you find the unit vectors of each of these guys? Well, the unit vector of A, the unit vector in A's direction, whoops, we're using different notation. The unit vector in A's direction should be 1 over root 13 times A, right? What about the unit vector for B? No, wait, sorry, not B, for C. Let's do the unit vector for C. For obvious reasons, I think you'll note. B's a go. I'm just checking that I did that right. Yeah, I think B's magnitude's right. So I would do 2 over root 13, that's the reciprocal, times this guy. And what if I simplified this? If I simplified this a bit, what would I get? I could multiply the 2 in, distribute the 2, and I get negative 3 comma 2. So what this shows, they have the same unit vector. A and C have the same unit vector. B would be the exact same thing. B's radical simplifies nicely, actually. It's 3 root 13. There we go. So then I'll do B. I'll find B's unit vector. Do you have any predictions? 1 over 3 root 13 times 9 comma negative 6 would also simplify to 1 over root 13 times 3 over negative 2. So what you have here is all 3 of these guys have the same unit vector. And this is what I mean when I say the unit vector is really that guy's direction. If vectors are parallel, they'll have the same unit vector. What's an easier way to show that? An easier way to show that before you do anything else on this problem, I'm just going to shrink things down really quick. If you had to show that without doing a single other thing, you could also notice for parallel. So, right, let's write some notes, I guess, instead. Parallel. So we should know we have the same slope. We should know we have the same unit vector. And then it's the other thing I said, I think in our very first video on this section, will be scalar multiples. Parallel vectors, okay? What do I mean? If A equals root 3 comma negative 2, what about B? Can I factor anything out? Is B a multiple of A? If I factor out B a little bit, if I factor the GCF out, what would I get? I would get 3 comma negative 2, which is 3A. So again, that's why B and A are parallel. This is why it's so important to understand unit vectors. It's why it's important to understand scalar multiples. Scalar multiples are keeping things parallel. It'd be a really easy proof that things are parallel if they happen to be scalar multiples. And that means they have the same unit vector, which is really helpful for the next problem. And the next problem is a popular kind of test question. Hint. Hopefully you're actually listening to the audio and not just speedrunning this. If I have A equals, I'm going to use standard basis notation now, plus 4J, and B was I plus 2J, find V where the length of V is 3 and V is parallel, a notation I've wanted to use for a while instead of spelling it out. Just parallel, that's all that notation means. You should remember from geometry. To 2A minus 3B, like that vector. So we're going to go over the directions here. All right, so vectors are magnitude and direction. Are we given a magnitude? Yes, right there's a magnitude. So that means we need to look for a way to figure out direction. And parallel means same direction, always been true. If we're supposed to be parallel to this, that's going to give us our direction. So let's start with finding 2A minus 3B. You should be able to do it right now. I'm giving you a chance. Pause the video. Find 2A minus 3B. 2A is negative 6I plus 8J. And again, if you wanted to turn this into component notation, I would be fine. Plus negative 3I minus 6J. I multiplied by the negative. Make sure you distribute the whole negative. And then when I add these two together, I'm getting negative 9I plus 2J. All right. So that's my vector V. Or sorry, that's my vector, let's call it W. That's W. So W equals negative 9I plus 2J. If you're trying to picture it, it'd be to the left. Okay. It should be shorter in that direction, right? It'd be, oh, you know, I got it right. If that's W. So W is a pretty long vector, spoiler alert, but it has a direction. All vectors have direction. So step 2, we're going to turn into a unit vector. Because again, what we're thinking about with unit vectors is these are pure direction. How do I turn it into a unit vector? You need to find the magnitude of W. Notice I'm not talking about the magnitude of V. I'm talking about the magnitude of W. We got to turn W into unit vector because we want W's direction. We want W direction. So this would be root 81 plus 4, which is root 85. And so the unit direction I want, the pure unit vector, would be 1 over root 85. And just to be clear, this is W over the length of W. That's the scalar multiple times negative 9i plus 2j. So what do we do in this step? We took a long vector W and we translated it into the unit vector in that direction. And then the third step is really straightforward. We're going to scale up or down. But in this case, it's scale up. So 3u. V equals 3u. 3 over root 85 negative 9i plus 2j. And that's it. So that's why unit vectors are useful. And that's some stuff we can do with them. In the next video, we're going to talk about some applications of these unit vectors and another way of talking about direction. Thanks for watching. See you in the next one. Bye.